In around 1800s, scientists were very curious to find that bats could fly and avoid obstacles in complete darkness. Do they have super sensitive eyes? No, because they found that even the ones which were completely blind could also do this, suggesting that they were not relying on their eyes. However, surprisingly, when they put a plug in their ears, temporarily making them deaf, they failed miserably. So, does this mean that bats see with their ears? Well, kind of. After a lot of research, people found that bats continuously emit pulses of sound of ultrasonic frequency. And ultrasonic means a frequency higher than 20,000 hertz. And because humans can hear up to a max of 20,000 hertz, you and I cannot hear this sound. And thank God for that. Otherwise, can you imagine how noisy it would be around bats? But how does this help? Well, when this sound goes and hits some obstacle, it reflects back. And the bats can hear this reflected sound. In other words, they can hear an echo of their own voice. Now, depending on how long it takes for these bats to hear their own echoes, they can estimate how far that obstacle is. For example, if it takes a long time for them to hear their echoes, it means the obstacle is far away. So no worries, they can chill. On the other hand, if it takes a very short time for them to hear their echoes, that means the obstacle is very close to them. So since they're using echoes to locate how far something is, we call this technique as, no surprise, echolocation. And bats are so good at echolocation, they can even tell whether these echoes came from a large tree or from a tiny moth, their favorite insect to feed on. And a fun fact about moths, since they're hunted by bats using this technique, using these high frequency sounds, their ears have evolved to be able to listen to these high frequency sounds. And so whenever bats are in pursuit of them, they immediately get to know and they try to evade them. And bats aren't the only ones that use echolocation. Turns out certain sea creatures like dolphins or whales also use them. The thing is, underwater, you can't see very far away. You may have noticed this if you've looked at some underwater footages. You can see things which are close to the camera, but things which are far away, you just can't see. And that's because light gets very easily absorbed by water. So light can only travel a small distance before getting completely absorbed. However, sound can travel a lot farther before getting absorbed. And that's why these animals have evolved to use sound and their ears rather than their eyes to navigate underwater. And for this very same reason, even the ships and submarines have stolen this technique to navigate underwater. They are equipped with devices that can generate high-frequency ultrasounds and which can also receive these reflected echoes. And just like with the bats, by calculating how long it takes to receive that echo, they can calculate how far that object is. And these devices are called sonar. It's an acronym for sound, navigation, and ranging, which basically means we're using sound to navigate or to move and avoid obstacles, and ranging, meaning to figure out how far something is. So while bats and dolphins have naturally evolved to use sonar, we use science to do the same thing. In fact, in this technique, just by using the formula of speed, we can calculate exactly how far something is. So let's take an example. So let's imagine we are inside this ship and we want to calculate how far the floor of this ocean is from our ship. To do that, we will send an ultrasound, and let's say we receive it after a time of 4 seconds. The speed of sound in water is something that people already know. It turns out to be roughly 1,500 meters per second. And so using this information, we want to calculate how far the ocean bed is from the ship. Let's call that distance as d. So how do we do this? Well, we know the formula to calculate speed. Speed equals distance by time. So using this formula, let's see if we can calculate what d is. In fact, can you try and do this yourself first? Pause the video and see if you can substitute in this formula and calculate what this distance is. Alright, since it's the sound that is traveling, the speed over here will be the speed of sound. So if we substitute for speed, we will get 1,500 meters per second. That equals distance. Now, distance traveled by the sound is not d, because notice the sound goes down and then comes back up again. So the total distance it travels is 2 times this value, 2d. So it travels a distance of 2d, and we know the time it takes to travel that distance, that is 4 seconds. Now from this, all we need to do is do some algebra and we can calculate what d is. Again, if you have not done this before, great idea to pause the video and see from here if you can calculate what d is. Alright, let's do this. So if you simplify, 2 goes 1 times, 2 goes 2 times. So let me erase the 2 from here. 2 goes 2 times over here. 2 seconds. Now since I want to calculate d, I want to get rid of this 2 seconds. I will multiply by 2 seconds on both sides of the equation. So I'll multiply by 2 seconds here. I will also multiply by 2 seconds over here. And so the 2 seconds will get divided. Over here, notice the seconds cancel out. And what I'm left out on the left hand side is 1500 times 2. 15 times 2 is 30. So this will be 30, and then 2 more zeros. 3,000 meters equals our d. So the floor of the ocean is 3,000 meters below the ship. And this is how we can use sonars and the formula of speed to calculate how far something is. So what did we learn in this video? We saw that echolocation is a technique used by bats and whales and ships to calculate how far something is. This is also called a sonar. And how does it work? We send out a high frequency sound and calculate how long it takes to receive the echo. Then we can use the formula of speed and figure out how far the object is. And guess what? Turns out that there are some blind people who have learned how to make sounds from their mouth and echolocate. That's pretty cool, isn't it?